Class, this toolbox will introduce functions and discuss their power as tools for studying just about anything you might encounter in earth and environmental sciences. In essence, when we discuss functions, we're discussing nothing more than a framework for talking about inputs and outputs. Those inputs and outputs will most commonly be numbers, but they don't have to be. They could really be anything. Okay, so let's talk about functions. At their core, functions are a relationship between a set of inputs and a set of outputs with the property that each input maps exactly to one output. You can think of a function as a box. You put something into the box, then the box does something to it, and then you get something else out. Most of the time, we think about functions where you put in a number and get a number out. But those are not the only types of functions we could have. A function could take a letter in and give you a matrix out. It could also take in a number and give you out a picture of a fruit. The function can take in a 9 and spit out a banana, and take in an 8 and spit out an apple. The key is just that if you give it an 8 once and it gives you a banana, it had better give you a banana every time you give it an 8. It can't play tricks on you by giving you a banana for an 8 one time and giving you an orange for an 8 the next time. Okay, next let's talk about function notation. Normally we write functions in the form of f of x equals something. In this case, f is the function name, and x is a variable that we use for the input. Let's go back to our function that takes in numbers and gives other numbers as output. It takes in a 2 and gives us a 4, and it takes in a 3 and gives us a 9. We could rewrite it in function notation as f of x. In this case, there's actually a numeric function underlying this. Our function is actually taking in a number and returning the square of that number. So we could write out the equation for our function as f of x equals x squared. You're of course used to encountering functions like this. We could also express this as y equals x squared, and we're used to thinking like that, and of course graphing it as well. If we want to evaluate this function, all you need to do is pick an input and plug in for it. For instance, if we plug in the value 1, we can calculate that 1 squared is 1, so f of 1 is equal to 1. If we plug in 4, 4 squared is 16, so f of 4 is 16. So why is it that we need to use this function notation? Why can't we just use the older format that we're used to of saying y equals x squared? Well, basically it boils down to the fact that using function notation gives us much more flexibility. For instance, let's say you wanted to extend that function backwards towards negative numbers, but when your value is negative, you actually want the negative of the value squared. You could write a function like this: g of x equals x squared if x is greater than 0, or negative x squared if x is less than 0. If we were to graph this now, we can see that we have a smooth function that increases rapidly, plateaus, and then increases again. When x is greater than 0, this graph is the same graph we would get if we graphed y equals x squared. But if x is less than 0, it's the same graph we would get if we graphed y equals negative x squared. We could also get more creative with our functions. As I said, functions don't have to return a number. We could write a function h of x, where h of x gives us an apple if x equals 8, it gives us a banana if x equals 9, and it gives us 0 if x is not equal to either 8 or 9. We can also write functions that have multiple inputs. For instance, this is the type of equation that we might use to quantify algae growth rates as a function of light, for which I've used the letter L, and nutrients, for which I've used the letter N. In this case, I'm referring to growth as the function g of L, n. We say that g is a function of L and n because both of these are inputs to g. The function says that growth is equal to 1 minus e to the negative L divided by 500, all times n over n plus 2. This function is actually a somewhat realistic equation for algal growth rates. The first portion of this equation tells us that growth will be a saturating function of the light level as quantified by this exponential equation. The second part of this equation tells us that growth will also be a saturating function of nutrient concentrations. In this case, we refer to the value 2 in the denominator as the half saturation constant for nutrient uptake. If we graph this function against both light and nutrients, we can see how the algae will grow as a function of light and nutrients. We can see that if either light or nutrients are very low, the algal growth rates will be close to 0. However, if they are both high, the growth will reach close to 0.8 per day, which actually means that the population would double approximately every day. Another powerful thing that we can do with functions is write functions of functions. Consider, for instance, some scientists studying this larval bluefin tuna. I have one friend named Estrella who studies the growth rates of these tiny tuna. She carefully dissects out these little tiny bones called otoliths from inside the ears of the tuna. These otoliths actually work like tree rings, so by counting the rings in the otolith, Estrella can figure out how old the tuna is. She also measures the length of the tuna, so this allows her to determine the length of the tuna as a function of age. Estrella determined that larval tuna length is a linear function of age with a slope of about 0.5 and an intercept of about 2.2 millimeters. So we could write a function that describes length as a function of age. We'll call the function g, and we'll make it a function of a for age. Our function is g of a equals 0.5 times a plus 2.2. I have another friend named Raul. Raul has been interested in the weight of larval tuna, so he has been going out and catching larval tuna, measuring their lengths, and then drying them out and weighing them. In this way, he's been able to determine the relationship between their weight and length. He found that the relationship was best described by an exponential function. We'll write it out as w of s equals 0.01 times e to the 0.6 times s. In this case, w is our function for weight, and s is the input variable that we'll use to stand for the standard length of the larval fish. Okay, so we've got these two functions. G of a calculates length as a function of age. W of s calculates weight as a function of length. I'm interested in how quickly these fish grow and hence how much food they need to eat. So what I really want to know is weight as a function of age. Luckily, I can do this easily using our function notation. I'm actually going to put one function inside of the other function. I'll calculate w of g of a. Thus, I've embedded one function inside of the other function. When you have one function inside of the other function, the way that you evaluate it is by first evaluating the inner function and then evaluating the outer function. So let's do a quick example. What's the weight of a 2-day-old fish? Well, we want to evaluate w of g of 2. To do this, we will first plug in the values for g of 2. We replace the a in the equation with 2, and then we calculate that 0.5 times 2 plus 2.2 equals 3.2. Now we simply have to evaluate w of 3.2 by plugging into our equation for w. We now have the equation w of g of 2 equals 0.01 times e to the 0.6 times 3.2. If I plug this into my calculator, I find that the weight of a 2-day-old fish will only be 0.07 milligrams. That's really all there is to it. We can also now, if we want to, use w of g of a to plot weight as a function of age. This graph now shows us weight as a function of age. We can see that the larval tuna starts off its life weighing about 0.06 milligrams, but over the course of a week it starts to grow rapidly, and after a week it weighs over 5 times its birth rate. Later in this course we'll talk about taking derivatives to actually calculate this fish's growth rate as a function of age. Then we could really figure out how much food this fish is going to need at different periods in its life. So far we've talked about a lot of different types of functions. Functions can be numeric, but they don't have to be. They can take a number and give us a matrix. They can take a letter and give us a fruit. We can write a function of a function. So what is not a function? Well, the key is that you can have only one output for any given input. Keep in mind that many different outputs can have the same input. You could write a function that says f of x equals 1. This would give you 1 as an output for every single input. However, consider the equation for a circle. The equation for a circle is x squared plus y squared equals 1. This equation, when plotted, of course, gives us a circle. Looking at this, we can see that there are two potential outputs for any specific value of x. For instance, if x equals 0, y can be equal to -1 or 1. Or if x equals 0.5, y can be equal to 0.86 or -0.86. Since some values of x can give you multiple values of y instead of a single unique value for y, this equation cannot be a function. Another important reason that we use function notation is because it allows us to easily talk about the inverse of a function. An inverse function basically reverses another function. So if we had a function f of x that takes in a 9 and gives us a banana, its inverse function would take in that banana and give us back a 9. And if f takes in an 8 and gives us an apple, then f inverse of x has to take in an apple and give us back an 8. Inverse functions basically give you back what you started with. We use the function we use the notation f -1 of x for inverse functions because raising something to the exponent of -1 gives you the inverse of that number. In mathematical terms, if g of x is the inverse of f of x, then g of f of x equals x, because the function g is simply undoing what the function f did. Let's consider a simple example. We will define the function f of x equals x cubed. We can graph this function and see what it looks like. So what is the inverse of this function going to be? Well, let's put up a figure and try plotting some points onto this figure to see what the inverse should look like. First, we'll calculate what f of 0 is. F of 0 is 0, so we can go and pretty easily put 0, 0 onto our inverse function plot. Next, let's try f of 0.5. F of 0.5 equals 0.5 cubed, which is 0.125. So f of x takes in 0.5 and gives us 0.125. That means our inverse function graph needs to take in 0.125 and give us back 0.5. So let's plot that on the figure. Next, we'll try f of 1. F of 1 is 1 cubed, which of course is 1. If f takes in 1 and spits back 1, then f inverse must do the same. So we can add a point at 1, 1. Now let's do the same thing for f of 2. F of 2 equals 8, so f inverse of 8 equals 2. Similarly, f of 3 equals 27, so f inverse of 27 equals 3. Of course, f of x equals x cubed is not the hardest function to analytically find the inverse of. If you had put in y equals x cubed and solved for x, you could pretty easily see that you just need to take the cubic root to find the inverse function. And if we graph the cubic root of x, we find that happily it does fall right along those points that we just calculated. So basically that's what the inverse function does. It takes in the output of your original function and gives you back your original input. And as we saw, if we want to graph an inverse function, all we have to do is compute the original function and then swap the inputs and outputs on our output function graph. This allows us to estimate what the inverse function will look like, even if we're not sure how to analytically solve it. However, it is important to note that not all functions have well-defined inverse functions. Consider, for instance, this function. If we calculate f of 0, we get 0. So that plots nicely onto our inverse function. However, what happens when we calculate f of 2? F of 2 is 37, but we can't actually go ahead and state that f inverse of 37 is 2, because if we look at the graph closely, f inverse of 37 would also have to be equal to approximately 4 and approximately 9. If we put 37 into f inverse would not actually know what to do. For this reason, we state that f of x does not have a well-defined inverse. That's it for this toolbox. Don't forget to take the mini quiz.